Assalamualaikum and good morning. My name is Muhammad Ismail Akif. Now I will talk about the introduction of multivariable HVAC control. The multivariable HVAC control projects optimize system performance by simultaneously managing multiple variables such as temperature, humidity, airflow, and more. This advanced approach compared to individual control leads to more efficient operation and energy savings. Multivariable HVAC control aims to maintain comfort such as temperature, humidity while minimizing energy use. This is achieved by dynamically adjusting system settings based on real-time sensor data and advanced algorithm like MPC, fuzzy logic, or neural networks. This algorithm predict future conditions and optimize control parameters accordingly. The system relies on a network of sensors such as temperature, humidity, air quality, and actuator like valve, damper, and fan to monitor and adjust the HVAC system based on this algorithm. Now I will talk about process description. First is design phase. Design phase is develop mathematical models or use data-driven approaches to represent the HVAC system dynamics. Second is hardware installation. Hardware installation install necessary sensors, actuators, and control hardware in the HVAC system. Third is integration and testing. Integration and testing is to integrate the implemented control system for smooth operation and data collection. After that is optimization and fine tuning. Optimization and fine tuning is continuous monitoring needed to monitor system performance using real time data. Last one is documentation and reporting. This approach will maintain detailed documentation of system design, installation, and operational procedure.
Assalamualaikum warahmatullahi wabarakatuh. My name is Noliana Amira binti Ahmad Fairuz. My metric number is B092110092, and I'll be explaining about the control system design, also instrumentation and calibration in HVAC system. So in control system design, designing multivariable HVAC control is challenging due to the complex interplay of factors such as humidity, temperature, airflow, and energy. So while offering more responsive and efficient operation compared to single loop controllers, it faces challenges like interdependent control variables, which are temperature, humidity, airflow, and energy. They are difficult to isolate and manipulate. Second, non-linear system responses and dynamic changes caused by external factors, which are occupancy and weather. The third one is balancing control choices within system constraints such as fan speed, valve placement, while optimizing energy consumption and comfort. In control system design, there are four main components in the HVAC system. So the first one is model predictive control, which is an effective method for managing restrictions and enhancing system performance through behavior and prediction. Second, robust control, to create controllers that are less sensitive to the unknowns and disruptions that come with HVAC systems. The third one is the third one is fuzzy logic control, which is utilized fuzzy logic rules to capture human expertise and handle non-linear system dynamics. And the fourth one is data-driven techniques, which is to identify systems, develop optimal control strategies, and implement adaptive control. So the next one is instrumentation and calibration. So in instrumentation in HVAC system, actuators are one of the main components of the HVAC system, which translate control inputs into physical actions. So for example, variable air volume boxes regulate airflow to different zones that dampers direct or restrict airflow. Moreover, fans control airflow velocity and volume, heating and cooling coils that regulate temperature and humidity, as well as pump motors to manage water flow for heating or cooling systems. These actuators will operate together to ensure that the HVAC system delivers the correct temperature, humidity, and airflow to each area of the structure. So in terms of calibration, one, two, three. So in terms of calibration in HVAC system, calibration is essential for the accuracy and dependability of the HVAC system. The sensors such as thermometer for temperature sensors must be calibrated to a known standard. So this procedure involves in determining a reference point which can create a calibration curve that compares the output of the sensors to the reference values, as well as changing the output of the sensors to compensate for any deviations from the ideal responses. So I'll be passing to Harit, my teammate. So that's all from me. Thank you.
Alright, without further ado, I will continue the presentation with modeling and control strategy. This diagram illustrates the main components and control strategies of our Hvac systems. Each block represents a core aspect with arrows indicating the flow of information and control between them. Our control strategies include PID, feed-forward, MPC, adaptive, fuzzy logic, and decentralized control methods. By integrating these strategies, we achieve optimal performance, energy efficiency, and adherence to safety and regulatory standards. Next, I will talk about the implementing steps. These are the flowcharts of our process. The implementing multivariable HVAC control involves several critical steps. First, we perform system identification by collecting data to model HVAC components accurately. Then, we design appropriate control strategies and simulate their performance in a virtual environment. Once verified, we apply these controllers to the actual HVAC systems. Continuous monitoring and optimization are essential to ensure the system operates at peak efficiency, leading to energy savings and a comfortable indoor environment. In conclusion, our project demonstrates the multivariable control for HVAC system significantly enhance system performance and energy efficiency. By integrating advanced algorithm and thorough system design, we can maintain comfortable indoor environments while minimizing energy consumptions. This approach not only benefits to the end users but also contributes to a more sustainable futures. Alright, without further ado, I will continue the presentation with modeling and control strategy. This diagram illustrates the main components and control strategies of our Hvac systems. Each block represents a core aspect with arrows indicating the flow of information and control between them. Our control strategies include PID, feed-forward, MPC, adaptive, fuzzy logic, and decentralized control methods. By integrating these strategies, we achieve optimal performance, energy efficiency, and adherence to safety and regulatory standards. Next, I will talk about the implementing steps. These are the flowcharts of our process. The implementing multivariable HVAC control involves several critical steps. First, we perform system identification by collecting data to model HVAC components accurately. Then, we design appropriate control strategies and simulate their performance in a virtual environment. Once verified, we apply these controllers to the actual HVAC systems. Continuous monitoring and optimization are essential to ensure the system operates at peak efficiency, leading to energy savings and a comfortable indoor environment. In conclusion, our project demonstrates the multivariable control for HVAC system significantly enhance system performance and energy efficiency. By integrating advanced algorithm and thorough system design, we can maintain comfortable indoor environments while minimizing energy consumptions. This approach not only benefits to the end users but also contributes to a more sustainable futures.